Hello friends, welcome to Joy of Life. So today we are going to do another medium level problem from Leetcode. The problem number is 94, binary tree in-order traversal. So this is one of the most common traversal method where you're given with the root. So given the root of a binary tree, return the in-order traversal of its node. Okay, so we'll be given the node of the tree and we need to traverse and then we have to come up with the in-order traversal. So in-order traversal means we'll visit the left first, followed by the root and then the right, right? So this is in order. So left, right, left value, right. So for a tree like this, what will happen is there is no left. So we'll exclude the current node 1 and then we'll go to the right. So 1 will be printed first, then we'll come to the right. So we came to a new node. We'll start exploring all over again. So we'll go to the left and from left we'll start exploring this node. So we'll try to go to the left. There is nothing to the left. So we'll exclude this current node itself. So we'll end up printing a 3. And then we'll try to go to the right of 3. So there is no right to 3 as well. So we are done with 3. We are completely. So we'll come back to 2. 2 is partially done. So 2's left was only visited, right? So we'll explore the 2. So we'll exploration means printing over here. So we'll print the 2 and then we'll try to go to the right side of 2. And there is nothing to the right. We come back to 1 and 1 was executing the right only, so there is nothing else. So what will happen is we'll have this order and this is going to be our in order traversal result. So if you see here that we have the result 1, 3 and 2. Similarly, it can be applied to any tree. So what we are going to do is, so we are going to look at the details and we are going to adhere to their constraint that they have given and the follow-up part as well here that recursive solution is pretty easy. So it is recommended that we do it in a iterative way, right? So let's check the iterative solution and we are going to map the recursive solution to the iterative solution and we are going to do the exact same thing as recursion using the call stack and we'll just mimic that same behavior using a normal stack. So this is a very important question for tree traversal and one of the things that you must know for a tree traversal along with pre-order, post-order and level order probably. There are different orders, so these three, four are the most important ones. So do check out the video after you have given a try and let's head over to the board and see how it goes. So what we have done over here is we have taken a tree like this, which has a root 1 followed by the 2 child 2 and 3, 2 has 2 childs 4 and 5, and then 3 has 1 child, that is 6. Right, and we are going to see the normal traversal algorithm. So this is a recursive algorithm that you see over here. So what do? Is we travel to the left, right? We start traversing from the root. So this is the root over here and we start going to the left as much as we can go over here. So this algorithm does not show you the null, but there is a requirement to check the null as well. So from 4, when we hit a null, what happens is we don't proceed any further, right? We come back from this function to here. So this left part was done for 4. So then we have the visit node. So visit node is the activity that you want to do for the in-order traversal. So in our case, we just wanted to print. So if we have to write this algorithm all over again for our case, so it will look something like this. So basically what we'll do is we'll traverse the node, same thing. Traverse will first go towards the left until it hits a null. And then for the visit node, we're just going to print. So what will happen is if I have to draw this tree, I just want you to understand that it will. So what will happen is we'll get the, so we cannot proceed any further to the left from 4. So we come back to 4 and then we print. So what will happen is we'll print a 4, right? And then we'll go towards 4's right. And again, from here we hit a null, right? And we come back. So 4 has completed all this statement and he has printed. So 2 was done till the left. Now what will happen from this position is the call will go back to 2, right? And now we need to do the things for 2. So what we are doing, we are just doing a print, right? And then from 2, we are done with the print, then we can go right? So from here, what will happen is we'll jump to 5 and 5 will again start to try its left. It can't. So it will come back from here. So I missed the arrow over here. It will also come back. Yeah. So it will come back and what we will do is after coming back, it's going to print the value and then it will try to go towards its right. And again, from right, we get a null. So 5 is done. So 5 will return back to 2. Now 2 has done both its left and right. So 2 is going to return it back to 1, right? So as we come to 1, 1's left part is done. So 1 will now go ahead and print the value that is required. So it will print a 1 and then it will execute this statement. So it will start going towards its right. So 1 will call 3, and 3 will again start going its left, but it has nowhere to go. It will get a null from here. So he will return, and then he's going to print himself. So 3 is done with the left and the printing part. Then what 3 will do is 3 will go to its right. So it comes to the 6, and 6 will try to go towards its left where it can't proceed. So it will get back, and it's going to perform the task, that is of printing. So we are going to print this value 6 over here. Now what will happen is 6 will try to check for its right, and there also it gets a null. So it's done. So it will return back to 3. So 3 is done on both, and 3 will return back to 1, and 1 has also completed. So at the end, what will happen is we'll have our in order result stored over here, right? If we just try to understand what has happened in this recursive algorithm is that we have a call stack, right, where the calls are maintained, right? So let's build a stack over here. So what will happen is basically I'll be called with the root. So I'm called with a 1, right? And as soon as I get a call, what I'll do, I'll execute the first statement to go to its left if it is not null. So I get a 2. And what I do is I call the same function all over again with this 2. So this 1 is going to get inside this stack over here, right? So 1 will come over here, and this place will be taken up by 2. So mind it that 1 is present inside my call stack. So when 2 comes, 2 will again call its left. So 2 will push himself to the stack, and what will happen is 4 will be coming here. So 4 has no left, right? So what will happen is it will execute the next statement as well. So what he'll do is he'll print himself. So he will print a 4, and what happens is 4 calls its right, but there is no right to it as well, right? So 4 is done. So execution of 4 is completed. So the moment it is done, this 2 is going to get popped out of the stack, right? This will come out. So 2 will come back out, and 2 after coming back has seen that it has done till here. So what 2 will do is 2 will print himself, and 2 will call its right. So 2 was popped out previously. So again 2 will push himself back into the queue, and what will happen is 5 will come into the picture. So 5 left is not there. So this statement will not execute. So what he'll do is he will print the values. So he'll print the values over here 5, and it doesn't have a write. So 5 is again completely done processing, right? So 5 will get out, and since there is nothing, we'll get element out of the stack. So 2 comes back again, right? And we see that, oh, 2 is done. 2 was the last statement was processing, it was done. So what will happen is basically 2 will get out and will pop from the stack once again. So what will happen is we'll get a 1. So in 1, what we'll do, this statement was done for 1, right? So we are going to print the value from 1, and what will happen is now we'll go to the right of 1. So this current function 1 will get inside the stack once again, and it will be called with a 3. We called with the right? So right, we have a 3. So 3 doesn't have a left, right? So what we'll do is this statement will not execute because of a null check, and then it will print its value. So it will print the value, right? So after printing the value, it will call its right. So what will happen is 3 gets inside the stack over here, and 6 gets called. 6 doesn't have a left, so it's not going to get inside this. So he's going to go ahead and print the value. So he will print a value of 6 over here, right? And now 6 will try to go to its right. It cannot go because there is no right. So 6 is also done. So we'll pop out 3. 3 will come out, and once we take 3 out of the call stack, we see that, okay, 3 was standing in its last statement, so it has completed. So 3 is going to get out, and we pop out again, and we get a 1. And once we get a 1, we see that, oh, 1 is also standing at its last statement. So 1 is also done. So at the end, what we see is that we get a result 425136, which is same as this one. So basically, we just simulated what the stack does, and we are going to do the same thing in the code as well. So what we'll do quickly is we'll move over to the board, and we'll just implement a stack of our own, and we are going to get the code working. We need to return a list of integer, right? So let's create that result that we are going to return at the end, and let's have an array list here. So what we are going to do first is we are going to check if root is null, then there is no point in processing forward. So in that case, we are just going to return the result. So we are going to return an empty array list in that case back from this function. right? And otherwise, what we talked about is a stack, and this stack should hold the tree node, right? And it will be, let's call it a stack. So I know that the root is there, it's not a null value. So what I'll do is I'll use a do while loop in this case because I know that values will be there. And we are going to iterate still the stack is not empty. Okay. We are going to add more condition to it, but let this be for the time being. And what we'll also do at the same time is we'll have a node called current and which will point to the root. And we will going to iterate until the stack is empty or current is not null, right? Because otherwise this will not enter the stack because our stack is initially empty. So we are going to put this bunch of exit criteria over here and we are going to proceed. As long as we are not getting a null on my left, we are going to push to the stack continuously, right? We have to go till the null and then we should come back, right? So current is initially at root. So until the current becomes null, what I'll do is I am going to put things into my stack. I just keep pushing things. And how this current is going to change iteratively. So current will be incremented in this fashion that current will become the next left element, left, we are going like this, right? So until we hit a null, right? So we will hit a null if we continue to go, right? So we'll jump and we'll finally end up having a null. And when we get a null, I am sure that my stack is not empty at that time. So once we come here, what we are going to do is we are going to pop element from the stack and we are going to get that element in the current. So if you see over here that what happened was once we hit that null, we took elements out and that became our current element, right? So we'll pop element and that item will become my current element. And then we need to execute the second part of the algorithm, visit the node or perform the activity, what we need. So we need to add to our result and we are going to put current.val into it. And then what we are going to do is we are going to set the current to its right. Whatever value it is, null, not null, we don't care, we'll set it to right. It will come over here again and it will start popping out things, right? That's what we want. And if it is not null, what will happen is again we'll start adding the left side of it, right? So this is the code all about. This is exactly the same thing that we have seen over here and discussed. So let us quickly run this code and check how it goes. It's a very straightforward and simple solution where it uses a stack where we are doing the simulation for a call stack. My bad that I have not returned the result. So yeah, so this is the pure simulation of the call stack that we have seen. So yes, it's been accepted. Let's see. Yep. So we got our result and it's uh, better than 100% of the submission and it virtually takes no time at all. So yeah, I hope you got the solution. You got the simplicity of the solution. This is a pretty simple solution and wherein once again what will happen is we'll have a runtime of order of n because we are visiting all the n nodes. And also in the call stack what will happen is we'll end up in the worst case we'll end up storing n nodes, right? So if you have a tree like this 1 2 3 like this, so you'll end up putting everything in your stack at one point of time. So for both space and time, it's going to be the same order of n complexity that we are going to see. So yeah, that's all from this video. I'll make another two videos on pre-order and post-order, which is going to be pretty much the same. So yeah, thanks for watching this video. Do like and subscribe and do share with your friends. And yeah, I'll finish this video over here. Bye bye.